Welcome to Tomorrow Unveiled,
All right.
where we take a stack of reports, articles, and white papers and turn them into something you can actually use. I'm your host, and I am ready to dive into what has been, frankly, a pretty wild week.
It certainly has. Good to be here. And wild is probably the right word, though I think maybe not in the way people usually expect when they hear news about space.
Right. Not just, a cool new rocket launch.
Exactly. We are looking at the week of January 22nd through the 29th, 2026. And if you take a step back and you look at the sheer volume of from propulsion breakthroughs to regulatory crackdowns, it feels like a watershed moment.
Watershed how?
Yeah.
Because we usually talk about incremental progress in this industry, a test here, a contract there. This feels different to you.
It does. It really does. I think for a long, long time, we've been in this phase of, let's call it experimental demonstration. Companies promising they can do things.
Lots of slideshows,
Yeah.
lots of concept art.
So many renders, and maybe a subscale test in a vacuum chamber somewhere. But looking at the stack the research team compiled for this week, we're seeing the shift. A shift to what I'd call operational permanence.
Operational permanence. Okay, break that down for me.
We aren't just testing if rockets work anymore. That's largely a solved problem. We're figuring out how to manage traffic jams in orbit, how to fix supply chains for exotic metals, how to deal with the safety realities when the sky gets crowded. It's the boring stuff.
The boring stuff that makes everything else possible.
That's it. It's the plumbing. It's the logistics. It's the stuff that turns a cool experiment into a real functioning economy.
Yeah, that's the mix that really stood out to me in the research stack this week. On one hand, you have this incredible golden age energy. NASA talking about nuclear rockets and engines that eat themselves, which sounds completely insane, and we will definitely get to that.
Oh, we have to.
But on the other hand, you have the gritty, unglamorous reality of it all. The logistics, frozen valves, water filters, acting up on a moon mission, and a very, very sobering accident report from the NTSB.
And that is the friction point. That is where the industry lives right now. And that's our mission for this edition of Tomorrow Unveiled. Our research team has stacked up everything. NASA press releases, NTSB accident investigations, financial reports on the titanium market. We want to understand not just how we are getting to space, but how we are building an actual economy and a safety net once we get there.
So it's sci-fi becoming real-fi.
I suppose you could say that. But as we'll see, real-fi comes with a lot more paperwork.
And a lot more waiting on the weather.
A lot more waiting on the weather and a lot more safety regulations. Yeah.
Which is probably a good thing, considering the energies involved. Okay, let's unpack this. I want to start in the engine room, because if we're going to have this space economy, we need to get there faster, cheaper, and more efficiently. And there were 3 massive stories this week about propulsion that seemed to cover, well, every possible way you can move a vehicle.
They really do cover the whole spectrum. From commercial aviation right here on Earth to deep space transit. It's pretty rare to see this much movement in propulsion tech in a single week.
Let's start with the one that feels closest to home, or at least closest to my next vacation flight. The research team flagged a major announcement from NASA and GE Aerospace about a hybrid electric engine. Now, when I hear hybrid, I think of a Prius. I think of a battery kicking in at a stoplight. Is that what we're talking about? Prius at 30,000 feet?
In a very high-level conceptual sense, yes, but the engineering is significantly more complex, and the stakes are, much, much higher.
I would hope so.
Yeah. This news comes out of a successful ground test at GE's facility in Peebles, Ohio. They've been working on this under a NASA project called HITECH.
HITECH.
It stands for Hybrid Thermally Efficient Core.
Of course it does. They love their acronyms.
They always do. But the breakthrough here is substantial. They took a commercial Passport turbofan engine. Now, context is key here. This isn't some small experimental drone engine. No. The Passport is the engine you'd find on a large business jet, a Bombardier Global 7500. It produces about 20,000 pounds of thrust. It's a serious piece of machinery.
Okay, so they took a real working jet engine and did what to it? Did they just strap a battery to the outside?
Well, that's the thing. It's so much more elegant than that. They didn't just strap something on. They actually embedded high-power electric motor generators directly into the engine core.
Inside it?
Inside it.
Yeah.
Specifically, they integrated them with the high-pressure compressor, which is, that's the heart of the engine. It's incredibly hot, incredibly high pressure. It's a brutal environment.
Okay, let's break that down. Unlike a car where the battery might drive the wheels, this is, helping the turbine spin.
Precisely. You've hit on it. Think of it as an electric turbo boost. In a jet engine, the hardest work, the most stressful part of the flight is takeoff and climb. You are fighting gravity, the air is dense, you're burning the most fuel, generating the most heat. The turbine is just working its guts out.
Right.
This system allows them to inject electrical power directly into the main shaft during those high-stress phases. It takes some of the mechanical load off the gas turbine.
So you use electricity to do the heavy lifting, and then you save the jet fuel for just cruising along at altitude.
That's a big part of it. But here's the aha moment that the research team really highlighted, and this is where it totally diverges from that Prius analogy we started with.
Okay.
This system doesn't necessarily need a massive, heavy battery pack to be effective.
Wait. How do you have a powerful electric motor without a huge battery? Where's the power coming from?
It's about power extraction and power transfer. The system is bidirectional.
Bidirectional, so it can go both ways.
Yes. When the engine is cruising efficiently at altitude, when it's just sipping fuel, the motor flips its function. It becomes a generator. It actually extracts excess energy from the spinning turbine.
So it's harvesting power from the engine when the engine isn't working that hard.
Exactly. It can then use that power for other systems on the plane, or, and this is the clever part, it can store it briefly and re-inject it later. It's about optimizing the thermodynamics of the engine cycle itself. You pull power out when the engine has excess spin, and you push power in when the engine is straining.
So it's less about a battery and more about energy management.
Yeah.
It's making the engine smarter, keeping it in its sweet spot across the whole flight.
You've got it. That's the perfect way to describe it. And the goal here, the number they're targeting, is a 10% reduction in fuel burn.
10%. Okay, I have to play devil's advocate here. 10% sounds, I don't know, a little incremental. Is all this incredibly complex engineering, embedding motors into a jet engine core, really worth it for just 10%?
In the airline industry, 10% is the holy grail. I cannot overstate this. Airlines operate on razor-thin margins. Fuel is usually their number one or number two operating expense.
Okay.
If you can cut fuel consumption by 10% across a global fleet of thousands of aircraft, you are talking about saving billions and billions of dollars, and not for nothing, millions of tons of carbon emissions.
Okay, when you put it that way, when you scale it up, it's not incremental at all. It's massive.
It's transformative, and the target here isn't private jets. NASA and GE are explicitly looking at single-aisle commercial aircraft. The Boeing 737s, the Airbus A320s of the world, those are the workhorses of the sky. They make up the vast majority of flights globally.
So this could be on the plane I fly on in, what, 10 years?
That's the roadmap. They're aiming for the 2030s, and the key is they're doing it without weighing the planes down with heavy batteries, which is the Achilles heel of all electric flight. Batteries just kill your payload capacity.
So it's not about flying on batteries alone, which we know is really, really hard. It's about making the gas engine smarter.
Correct. It's optimizing the thermodynamics.
Yeah.
And the fact that they've done this on a modified production engine, not just a lab simulation or some, computer model, that's a huge step towards certification. This is real hardware.
Okay, so that's getting us around Earth more efficiently.
Mm-hmm.
But the second story in the stack is about getting us somewhere much, much further away. This one involves the word nuclear, which, usually makes people sit up straight.
It does, for good reason. We're talking about the Nuclear Thermal Propulsion, or NTP, revival. This week, NASA's Marshall Space Flight Center, along with their partners at Lockheed Martin and BWXT, completed a successful cold flow test of a nuclear thermal rocket engine.
Cold flow sounds safe. I'm assuming that means they didn't actually turn on a nuclear reactor in Alabama.
You assume correctly.
Right.
And that's a critically important distinction. This test unit is what they call an engineering development unit. It's roughly the size of a 100-gallon drum. The goal of this test wasn't to split atoms. It was to validate the fluid dynamics.
Fluid dynamics, so basically plumbing.
The highest stakes plumbing in the universe. In a nuclear thermal rocket, you aren't burning fuel in the chemical sense. You are taking a propellant, usually liquid hydrogen, which is incredibly cold, near absolute zero, and you're pumping it through a reactor core that is incredibly hot, like thousands of degrees hot.
And that heat just flash boils the hydrogen.
It flash expands it into a gas, it shoots out the nozzle at tremendous velocity, and that's what gives you thrust. The cold flow test is just checking if the pumps, the turbines, the pipes can handle the liquid hydrogen without the reactor actually being hot.
So they're just making sure the pipes don't burst before they add the dangerous part.
Right. They need to prove that they can pump the cryogenic hydrogen propellant through the engine core at the insane pressures and speeds required without it leaking, cavitating, or, blowing up before they ever introduce radioactive material. If the plumbing fails with a live reactor, you have a very, very bad day.
A really bad day.
If it fails now, you just have a very cold, very expensive mess.
Why do we need this? I mean, we've been using chemical rockets, burning gas and oxygen, since the dawn of the space age.
Yeah.
The Saturn V got us to the moon. SpaceX uses methane. Why go nuclear and deal with all the, the regulatory headaches and the public perception issues?
It's all about the tyranny of distance and the fundamental limits of chemistry. Chemical rockets have pretty much hit a plateau in their efficiency. Right now, with our best chemical rockets, a trip to Mars takes 7 to 9 months. And that's only when the planets are aligned in a specific way, which happens every 26 months.
7 to 9 months in a tin can.
7 to 9 months in a tin can being bombarded with deep space radiation, which degrades your DNA. 7 to 9 months in microgravity, which destroys your bone density and your muscle mass. And 7 to 9 months of psychological isolation with the same 3 people.
And nuclear changes that math.
Drastically. Nuclear thermal propulsion is significantly more efficient. In rocket terms, we talk about specific impulse, or ISP. It's basically the engine's miles per gallon. Chemical rockets top out around 450 seconds of ISP. A good nuclear thermal engine can hit 900 seconds, or even higher. It produces much more thrust for the same amount of fuel carried.
So double the efficiency. What does that mean for the trip time?
Estimates suggest it could cut transit time to Mars by half.
Half. So we're talking maybe a 3 or 4 month trip.
Potentially. And that is a complete game changer for crew safety. The less time you spend soaking up radiation in the void between planets, the better your chances of arriving healthy.
It's amazing that this tech has been around for so long. The research note said this was looked at in the 60s.
Oh yeah, the NERVA program, they built them, they tested them in the Nevada desert, they worked, but they never flew. The Apollo program was winding down, budgets were cut, and the political will just wasn't there. To see a full-scale validation of the hardware now in 2026 signals that NASA is finally getting serious about the actual mechanics of a Mars mission, not just the concept art.
It's amazing to think we're dusting off 1960s blueprints and finally making them work with modern materials and modern computers. But speaking of materials, the third propulsion story is the one that really made me do a double take. This is the European innovation section of our research.
Yes. The self-eating rocket.
I mean, come on, a rocket that eats itself. This sounds like something out of a horror movie, not an aerospace engineering lab.
It's a technology called autophagy. It sounds wild, but the physics are brilliant. The European Commission just awarded a pretty significant grant for this, specifically to a project called Alpha Impulsion's Sharpness.
Explain it to me like I'm 5, or maybe 10, because my brain is stuck on why would you eat your own vehicle?
Okay, think about the rocket equation that we always mention. It's the fundamental curse of spaceflight.
Right, the tyranny of the rocket equation.
To get to space, you need fuel. But fuel has weight, so you need more fuel just to lift that fuel, but you also need a big, heavy tank to hold all that fuel.
And once that tank is empty, it's just dead weight. It's a huge metal balloon you're dragging towards space for no reason.
Exactly. In a traditional rocket, you solve this by just dropping the empty stages off. You pollute the ocean, or you create space debris with these empty metal tubes. An autophagy engine, on the other hand, consumes the rocket's fuselage as fuel.
Wait, the body of the rocket is the fuel.
Precisely. The body of the rocket is made of a solid propellant composite. You can think of it like a hard, burnable plastic rod. As the rocket climbs, the engine is mounted on a track, and it effectively eats its way up the rocket from the bottom.
So the rocket actually gets shorter as it flies.
Exactly.
Yeah.
It completely eliminates the problem of dead weight because the structure is the propellant. As you burn the fuel, you are also burning the tank. By the time you reach orbit, there is almost nothing left but the payload.
That solves the space debris problem instantly.
It does. There's nothing left to discard. It consumes everything.
That is just, it's so elegant. It's a total rethink of what a vehicle even is. It's like driving a car where the gas tank is made of gasoline.
It is. And while it's still in the early experimental phase, the fact that European partners are putting serious money, we're talking nearly €1 million in prize money plus development grants, behind this shows they are looking for a way to leapfrog the current technology.
They don't want to just copy SpaceX.
And no, they can't. They know they can't easily catch up on reusable liquid rockets, so they're trying to change the game entirely. They're betting on a complete little different paradigm.
So we've got engines that sip electricity, engines that run on nuclear heat, and engines that eat their own tails. It really does feel like the engine room is innovating at an incredible pace. But all these new engines are pushing things to places that are, well, currently a little bit chaotic.
And that brings us to Section 2, the moon, the station, and the humans.
Let's start with Artemis a second. This is the big show, the first time we're sending humans back around the moon in over 50 years. The research team noted that the massive SLS rocket and the Orion spacecraft were rolled out to the launch pad around January 17th. It's sitting there. It's real. It's not a render anymore.
It is real. And seeing a rocket on the pad, it just changes the psychology of the whole thing. It stops being a project and it starts being a mission. The schedule is tightening up. They're targeting a wet dress rehearsal.
That's where they fuel it all up, right?
Right. They load it with all the super cold fuel, the liquid hydrogen and oxygen, and they practice the entire countdown all the way to T-0. They just don't light the engines.
A full dress rehearsal.
Exactly. And they're targeting that for roughly January 31st. If that goes perfectly, they are looking at a launch window opening as early as February 6th.
But, and there's always a but, with spaceflight, we are dealing with some friction points.
Right?
The first one being winter in Florida.
Yes. Physics doesn't care about our schedules.
Yeah.
The research team highlighted the safety rules regarding temperature. Specifically, the temperature at the launch pad needs to be above 41.4 degrees Fahrenheit.
41.4. That seems oddly specific. Why not 40? Why not 42?
It has to do with the thermal limits of the seals and the propellants themselves. We all remember the painful lessons of the Challenger disaster.
The O-rings.
The cold O-rings that lost their flexibility. NASA is, understandably, incredibly risk-averse regarding temperature now. The SLS uses massive amounts of liquid hydrogen and oxygen. When you load that stuff into a rocket, the outside of the rocket gets freezing cold. If the ambient air is also too cold, you can have issues with valves freezing shut, with seals cracking, or with ice building up in places that absolutely shouldn't be.
It's just a reminder of the fragility of these massive machines. They can withstand the vacuum of space and incredible forces, but a chilly Florida morning can ground them.
It's a total paradox. But they will not launch if the numbers aren't green.
And then there's the water issue. The research team flagged something about total organic carbon in the crew's water system. This sounds bad.
This is one of those critical life support details that usually gets glossed over in the big headlines. The Orion capsule has a closed-loop life support system. The crew, that's Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen from Canada, they need water for this 10-day mission.
And they can't just bring a bunch of water bottles.
Not enough, so they recycle it. During the final testing, engineers found levels of what they call total organic carbon that were higher than the specification.
Is that dangerous? I mean, are we talking about poison?
Not necessarily toxic in the immediate sense, no, but in a closed-loop space system, organic carbon can essentially mean bacteria food. It can lead to biofilm growth inside the pipes.
Huh.
Exactly. In a closed loop where you can't just stop at a 7-Eleven for a bottle of Evian, water quality is paramount. If the crew gets sick with some kind of stomach bug 3 days into a lunar flyby, the entire mission is compromised.
So what are they doing about it?
They are swapping out the filters, they're flushing the entire system and retesting over and over until the numbers are perfect. It's a tiny detail, but it shows you the level of scrutiny. When you are sending 4 people to the moon, the water has to be perfect.
And what about the crew themselves? The report says they're in quarantine now.
Yes, it's called the Flight Crew Health Stabilization Program. They're in quarantine at Johnson Space Center in Houston, doing final simulations, final suit fitting checks. They'll fly to Kennedy Space Center a few days before launch. It's getting very real for them.
Yeah.
No more public appearances, no more shaking hands, just focus.
So while Artemis is gearing up, the International Space Station, our current house in orbit, is having a bit of the scramble. What's going on with the crew swap?
This is a perfect example of how spaceflight is still managed day by day, not month by month. NASA and SpaceX have had to accelerate the timeline for the launch of Crew 12 because Crew 11 is returning early.
And why are they coming home early?
The official reason given was a specific medical concern with one of the Crew 11 members.
The sources were pretty vague on the details of that.
And they will be, and rightfully so, because of medical privacy laws. But the operational impact is significant. Crew 11 splashed down off the coast of California near San Diego, specifically earlier than was originally planned.
And that leaves a gap on the station.
It does.
Yeah.
You never want the station to be understaffed for too long. The maintenance schedule is relentless. Experiments need to be run. So to fill that void, Crew 12 is being pushed up to a mid-February launch target.
It just shows how interconnected and fragile the whole system is. One person has a medical issue, and the entire global logistics deck gets reshuffled. Launch dates for rockets move, splashdown zones change.
Exactly. It's a very fragile ecosystem.
Amazing.
And speaking of fragility, we also got some news about Haven 1. This is supposed to be the first commercial space station built by a company called VAST.
Right, the private successor to the ISS. We've been hearing a lot about this.
Well, the timeline is slipping. Its launch date was targeted for 2026, but the research team confirms it's now been pushed to the first quarter of 2027.
What's the holdup? Is it money? Is it technology?
It's the sheer brutal reality of life support. Building a house in space is so much harder than the PowerPoint suggests. The transition from government-run stations like the ISS, which took decades and hundreds of billions of dollars to build, to private commercial stations, is happening, but it's happening slower than the investors might want.
It's not just launching a tin can into orbit.
Not at all. It's about air scrubbing, thermal control, radiation shielding, waste management. VAST is realizing that if they launch early and something breaks, it kills their entire business model. No one will want to visit the station that had a life support failure.
Better to be late and safe than early and, well, catastrophic.
Precisely. The market will wait for a safe station. It will not forgive a dead one.
Okay, that's a lot to think about with our current human presence in space. Before we jump into the next section, which is honestly mind-blowing regarding the sheer amount of data we're about to beam from space, I want to take a quick second for our viewers on YouTube. If you're finding this insightful, please take a moment to like this video, subscribe to Tomorrow Unveiled, and consider hitting that new hype button to help us reach more viewers. And of course, be sure to turn on notifications so you never miss an update on the future.
And we really do appreciate the support. It helps us keep the research team digging through these thousands of pages of reports.
Okay, Section 3, the data war. We usually talk about Starlink when we talk about space internet. It's sort of become the Kleenex of the industry, the default name for it.
It has.
But this week, a new challenger entered the ring, and they're bringing some very, very heavy artillery. Blue Origin announced Terrawave.
This is a major pivot for Blue Origin. We usually think of them for their New Shepard tourism rocket, the one William Shatner went up in, or the upcoming New Glenn heavy lift rocket. But Terrawave is something else entirely. It's a constellation of 5,408 satellites.
5,000 satellites. That's massive. But how is this different from Starlink? Is Jeff Bezos just trying to stream Netflix faster than Elon Musk?
No, and that's the key differentiator. The research team highlights that this is not a consumer play. You and I won't be buying a Terrawave dish for our RV or for our roof. This is an enterprise network.
Enterprise, meaning for businesses.
For big businesses, for governments, for logistics companies. And this is the big one for massive data centers.
The specs that the research team pulled mentioned optical interlinks. Are we talking about lasers?
We are talking about lasers in space, connecting the satellites to each other. They are claiming speeds up to 6 terabits per second.
6 terabits per second. I can't even process how fast that is.
It is an insane amount of bandwidth. To put that in perspective, a standard fiber optic connection for a whole office building might be a few gigabits. A terabit is 1,000 gigabits. We are talking about data pipes that can move the entire Library of Congress in just a few seconds.
Why on Earth, or off Earth, do we need that kind of speed in space?
One acronym, AI.
Of course. Here's where it gets really interesting. Why does AI need space lasers?
Because AI processing requires two things in massive quantities, data and compute power, and more importantly, it produces a third thing in massive quantities, heat. Data centers on Earth are already struggling. They consume the power of small cities. They need millions of gallons of water for cooling.
They're reaching a physical limit.
They are. We're seeing this trend toward the concept of data centers in space. Imagine putting the servers in orbit. You have unlimited solar energy. The sun never sets if you are in the right orbit. You have the infinite cold of space for cooling, which removes the single biggest operational cost for data centers on Earth. To make that work, you need a way to get the data up and, more importantly, get the answers down instantly.
So Terrawave isn't just internet. It's the high-speed extension cord for an orbital cloud.
That is the business model, precisely. It effectively builds the backbone for an off-planet internet. And they're serious about it. The deployment is scheduled to begin in late 2027, and it relies entirely on their own New Glenn rocket being ready. It's a huge gamble, but if the AI economy continues to explode, the demand for this kind of bandwidth will be there.
But, and this is the but that keeps coming up, where are we putting all these things? We just said there are over 5,000 new satellites from Terrawave. SpaceX just launched its 11,000th Starlink satellite. Amazon has Project Kuiper, which is now called Amazon Leo, and they're putting up over 3,000 more.
We are facing a congestion crisis. It's undeniable. The research team pulled some recent data regarding the Amazon Leo satellites. Astronomers are raising red flags, big ones, because these satellites are currently exceeding the brightness standards that were agreed upon.
So they're too shiny.
They are too bright. They reflect sunlight, and because there are so many of them, they are creating bright streaks across long exposure telescope images. It's actively disrupting ground-based astronomy. If you're a scientist trying to spot a faint, potentially hazardous asteroid, you don't want 1,000 Amazon satellites photobombing your data.
So is the night sky changing forever? I mean, is that a dramatic question?
No, I don't think it's dramatic at all. I think we have to be honest and say yes. We are trading a pristine, dark view of the cosmos for a global terabit-speed AI nervous system. It's a trade-off. And with Terrawave now adding another 5,000-plus objects to that, the sky is going to get very, very crowded.
It seems like every week the number of objects up there just doubles. Which feels like a perfect segue to Section 4, the orbital circular economy. Because if we keep throwing stuff up there, we're going to turn low Earth orbit into a high-speed junkyard. But there was some good news this week about cleaning up and recycling.
There was. And it starts with a really interesting company called Varda Space Industries. They successfully landed their W5 capsule at a test range in South Australia this week.
Varda is the company that's doing manufacturing in space, right?
Correct. They are trying to prove what they call the FedEx loop of space. You launch raw materials, you process them in the perfect vacuum and microgravity of orbit, and then you bring the finished high-value product back down.
Why manufacture in space? What can you make up there that you can't make down here?
The big one is crystal formation. Without gravity constantly pulling things down, crystals can grow larger and with far fewer imperfections. This is huge for the pharmaceutical industry making more potent, more targeted drugs, and for things like fiber optics and semiconductors. But the hard part isn't making the stuff. The hard part is bringing it back home without it burning up on reentry.
So what's the aha moment with this landing this week?
It's the heat shield. They used a material called sea pica, which is a conformal phenolic impregnated carbon ablator. Now that's a mouthful.
It is?
But the important part is that this was originally NASA technology, but this was a commercially manufactured version.
At work.
It survived re-entry at Mach 25. That's 25 times the speed of sound. Temperatures on the outside of that capsule exceeded 7,000 degrees Fahrenheit. The fact that a commercial startup can now manufacture a heat shield that survives those conditions is a huge milestone. It proves that this business model is viable. You can cook up valuable things in space and actually bring them home safely and relatively cheaply. It closes the loop.
So we can bring the good stuff down. But what about all the junk we leave up there? The dead satellites, the Erd rocket stages?
That's where the cleaners come in. The research team noted that a company called Starfish Space won a massive contract, over $50 million, from the Space Development Agency.
I love the name Starfish. What's their mission?
Their spacecraft is called the Otter.
Even better. I'm sold.
The Otter is designed to be a space tug. Its mission is to dock with dead military satellites and deorbit them. Essentially, it grabs them and drags them down into the atmosphere where they can burn up safely over the ocean.
It's a space garbage truck.
A very sophisticated, very autonomous garbage truck. It uses electric propulsion to rendezvous with an object that might be tumbling out of control. It has to clamp onto it, stabilize it, and then dispose of it. It's an incredibly difficult robotics problem.
And then you have other companies like Orbit Fab and Astroscale that are pushing for refueling in orbit.
The gas stations in space. Orbit Fab is developing the interfaces, the gas caps, effectively, so that future satellites don't have to die just because they ran out of fuel, which is the leading cause of death for satellites today.
So what does this all mean when you put it together? Varda, Starfish, Orbit Fab.
It means we are finally moving away from the throwaway culture of space. For 60 years, the model has been launch a satellite, use it until it breaks or runs out of gas, and then just let it die. Leave it up there as junk. Now we are building a fleet that can be refueled, repaired, recycled, or at least responsibly disposed of. It's the beginning of a true circular economy in orbit.
Which is absolutely necessary if we're planning to launch another 5,000 Terrawave satellites. Before we get into the really heavy stuff, the NTSB report, I want to ask our audio listeners for a favor. If you're listening on a podcast service like Apple Podcasts or Spotify, we'd be incredibly grateful if you could leave us a rating and review for Tomorrow Unveiled. It truly helps us reach new listeners and keeps the lights on in the studio.
It really does make a difference. We appreciate it.
Okay. Section 5, Systemic Risks. We've talked about the shiny, exciting future. Now we need to look at the cracks in the foundation. And the biggest crack this week came in the form of a report from the NTSB regarding a tragedy that happened about a year ago in January 2025.
This is a somber read, but it's absolutely crucial for understanding the safety landscape we're building. The NTSB released its final findings on the mid-air collision near Washington, D.C. that involved a regional jet and a Black Hawk helicopter.
67 people died. It was a horrific event.
Oh.
Why are we discussing an aviation accident in a deep dive about space?
Because airspace is a finite resource, whether you're at 5,000 feet or in low Earth orbit. As we discuss thousands of new satellites, launch vehicles that are returning to their launch sites, and the future of air taxis or eVTOLs, this accident is a grim, grim warning about congestion and management. The NTSB's findings were damning.
What were the key failures they identified?
Systemic failures. That's the direct quote. It wasn't just one pilot's mistake. The helicopter route was designed too close to the airline runway approach at Reagan National Airport. There was a dangerous over-reliance on see and avoid.
Just pilots looking out the window?
Exactly, just pilots looking out the window in one of the most complex and crowded airspaces in the entire world.
In 2025,
Whoa.
we're still relying on eyeballs.
We are. And the big sky theory, the old idea that the sky is so big that planes are unlikely to hit each other, is officially dead. The NTSB report highlighted altitude discrepancies, where the helicopter pilot might have thought they were at a safe altitude due to their altimeter settings, while the air traffic control tower thought they were somewhere else.
And the tower was understaffed. I remember hearing that.
The report mentions overwhelmed controllers. Now, project that forward. When you add the complexity of commercial space launches, which shut down huge swaths of airspace for hours at a time, to an already strained aviation system, you see the risk. We need rigorous digital tracking, automated deconfliction, and a total overhaul of how we manage the sky. We cannot rely on a pilot visually spotting a drone or a returning rocket booster.
It's a wake-up call. If we can't safely manage a helicopter and a jet in Washington, D.C., how are we going to manage thousands of autonomous vehicles in every city?
Precisely. The report implies that the technology inside the cockpit has massively outpaced the technology in the control tower.
And the risks aren't just in the air, they're in the supply chain, too. The research team flagged something they called a titanium crunch.
This sounds mundane, but for the aerospace industry, it is a crippling problem. Titanium is the metal of choice. It's light, it's incredibly strong, and it is extremely heat resistant. You cannot build high-performance jet engines or rocket components without it.
And currently, it's hard to get.
Very hard. The shortage is actively delaying engine and airframe production for companies like Boeing and Airbus.
Why? What's the
It's
cause?
geopolitics. We are, as an industry, trying to reduce our reliance on titanium from Russia and China, who have historically been the major producers. But you can't just snap your fingers and open a new titanium mine and processing facility. Ramping up production elsewhere, the research notes initiatives by Neocorp in the U.S. and AeroEdge in Japan, that takes years.
So prices are up.
Skyrocketing. But it's not just a shortage of metal, it's a shortage of people. The report notes that 29% of the entire aerospace workforce is over 55 years old.
Wow. That is a staggering number. Nearly a third of the workforce is nearing retirement.
We are facing a brain drain of epic proportions. We are running out of experienced machinists and engineers at the exact moment we are trying to build nuclear rockets and complex optical satellite networks. It's a systemic risk that money alone can't fix. You can't 3D print 20 years of hands-on experience.
That's a lot to process. We have the highest tech imaginable being held back by a lack of raw metal and gray hairs retiring.
It's the central paradox of the industry right now. We are reaching for the stars with one hand and trying to find our reading glasses with the other.
So let's try to summarize this watershed week. What's the big picture here?
I think the big picture is convergence. We have these incredible engines that are breaking the laws of what we thought was possible. Hybrid electrics, nuclear thermal, autophage. We have this digital infrastructure scaling up to terrifying levels with Terrawave and Starlink. But all of that ambition is tethered by these very real, very earthly problems. Frozen valves on the launch pad, medical emergencies on the station, supply shortages in the factory, and the tragic, urgent need for better traffic management in our own sky.
So we are building the future, but we're building it on a foundation that needs some serious reinforcement.
That's a very good way to put it.
I want to throw a question out to you, the listener. We love hearing your thoughts. Whether you're on YouTube or your favorite podcast app, leave a comment and let us know what you think about this idea of data centers in space. Would you trust your data orbiting at 17,000 miles an hour? Or does the idea of a server farm in the sky sound like a disaster waiting to happen?
I am genuinely curious to see the responses to that one.
Before we sign off, I know you always have one last thing in your notebook, something the research team found that we didn't get to cover. The final provocative thought.
I do. And this connects directly to that idea of trusting the network. The team found a fascinating detail about some new quantum sensing experiments being developed at Purdue University. They are looking at navigation that doesn't require GPS.
Navigation without satellites?
By using the quantum properties of atoms to measure acceleration and rotation with an insane degree of precision, an inertial navigation system that doesn't drift. And here's the thought. As we clutter the orbit with 10,000, 20,000, maybe 50,000 satellites, as we build this massive Terrawave grid that everything depends on, the most valuable technology might actually be the one that allows a spacecraft to fly completely blind, to navigate perfectly, independent of the very network we're building.
So we are spending billions and billions to build this grid, and the next big thing is the tech that lets us ignore it completely.
Are we building a grid we are destined to outgrow? Are we building the next great single point of failure? It's something to mull over.
That is a provocative thought to end on. Flying blind might be the safest way to fly. Thanks for listening to Tomorrow Unveiled.
See you next week.